Hello, good morning, good afternoon, and good evening, wherever you're joining from. Welcome to this new webinar in our series. My name is Andreas Rauber from the Vienna University of Technology, co-chair of this working group. I'm very glad to have today Maria Silvello with us, who will be presenting a webinar not on an entire implementation of our recommendations in a specific domain, but who will focus rather on one very specific recommendation, which is the automatic generation of basically human readable and machine processable citation text snippets that actually act as a link between the data, the query, and what we put into a bibliography, into a reference, into a citation. And he'll also show us a number of examples how this can be done for all kinds of different data sets, from rather simple tabular data up to very complex hierarchical XML schemas. And he'll also give us some demonstration of how this has been done in a number of actually deployed systems. So I'm very, very happy to have you here today, Maria. And what we'll do is we'll first go through the presentation. If you have got any questions during the talk, you can type them into the questions window that you will find in the pull-down menu on the right of the webinar interface. And then after the meeting, we'll go through the question one by one, and I'll hand over the microphone to you so that you can then enter into the discussion. So we will postpone this until after the core presentation. And with that, and without much further ado, Maria, thank you very much for being here today, for giving this presentation, and I hand over the microphone to you.
Okay, thank you, Andreas. So, hi everybody. So I'm going to talk about automatically generating citation text from queries. So it's recommendation 10 of the RDA recommendations, and this is the outline of my presentation. Basically, I will start by a brief introduction about data citation, but we are all well aware about its importance and why we need to cite data. Then I will focus on three key aspects of data citation. It's basically I will present a system for citing RDF data, so graph databases, then for citing XML data and relational databases. Basically, the presentation will be increasingly detailed. Let's say that the part about RDF will be very general, then we are going into a little more details for XML, and the part about relational databases will be a little bit more technical, if we have time for that. And for each specific model, I will talk about a specific use case where we tested our systems, and that's it, and then I will conclude. So, oh yeah, and these are below the slides, you can find some references, and at the end of the presentation there is the list, so you can look at the references that are expanding the concepts I'm describing here. So basically, the starting point is that publication is changing and information is increasingly published on the web. So a lot of information that we use in our experiments and in research are in curated databases that are created by experts, and so these data sets are complex, structured, and evolving through times. And the key point is that contributors need to be acknowledged for their work. And here we see some data sets like Eagle Eye about biological resources, IUFAR, BPS about pharmacological data, Reacton, which is a pathway database, and so on. But why data citation is important? First of all, as I said before, to give credit to data creators and curators, and also to institutions that invest in data creation. Then, for repeatability, reproducibility, and generalizability of research. This is a hot topic in several fields. I'm from the information retrieval field, and there we are talking about reproducibility in the last years. For instance, at the European conference in IR, there is a specific track about reproducibility, but also in the database community, they have this concept. And so the point is that if we publish a paper, we must be able to reproduce the experiment in that paper. And to do this, data citation is a key feature that we need for a successful reproducibility. And the citation is also needed for referencing data in order to identify, discover the data, and also retrieve the data we use. And of course, for building and propagating knowledge as traditional citations. So when we talk about data citation, there are some desiderata that we want to, that we need, and it's that, first of all, from my point of view, is that the generation of human and machine readable citations should be automatic, and then we will see why. Then the cited data should be uniquely identified, for instance, by means of digital object identifiers, ARC, or other identifiers. And citing data should be easy. Something like click, generate, copy, and paste the citation and the reference. We cannot expect people to, access our data and then know enough about the data set to select the relevant information to build a proper data citation and then write it down and use in their papers, because it's too much work and it's too much knowledge. So we need to ease this process. And another thing is that setting up and maintaining a citation system should require low or no effort at all for data creators and curators, because they are doing a lot of work for creating the data sets and to maintain the data set. We cannot ask them to add more work to cite the data. It's something that is very hard to do and there are no resources, so we should keep the effort and the resources required to a minimum. And so we focus on this specific aspect, which is the automatic creation of citation text and snippets. So we assume to have all other aspects implemented, like versioning or unique referencing to data and so on. So once we are able to deal with all those aspects, how do we automatically create a citation snippet, starting from a general query to a dataset? And a citation snippet is basically a collection of information, such as author's title, date, and so on, and some kind of access mechanism to the data. So we may think to a traditional citation, a traditional reference. To a paper, we have the title, the authors, the journal, pages, and so on. So for data, we have to find something similar to this. It's related to data provenance, if somebody of you is accustomed with that concept, but it's not exactly provenance. These citation snippets must be self-contained and immutable, and of course within some choice of format. And as I said before, we need this for a variety of reasons, like kudos, currency, authority recognition, and so on. So why the generation of citation snippets should be automatic? The first reason is consistency. There are studies showing that if we let users create their own citations, these references would be very heterogeneous, so they would be hard to automatically process. It would be hard to use these citations for bibliometric reasons and so on. So for consistency reasons, and if we create these citations automatically, we know that we are creating all citations equal, let's say. For simplicity, as I said before, because if we have an automatic way to produce citations, we do not have to ask users to know how the dataset is structured, which information is relevant for the citation, and so on, and for completeness, which is related to consistency. But basically it means that if we do this automatically, we know that each single citation to a dataset is complete of all the information we need to retrieve, access, and then reuse the data that are cited. And this aspect of data citation has been recently stated as a computational problem in the CACM in September of 2016. And basically, the thing of how we extract the data, how we retrieve all the relevant information about the data set we want to cite in order to create a citation, and how we do this in an automatic way is considered a computational problem. So we started from this consideration to do our work. And the first thing we focused on is that we have many models that are out there, And if we think about scientific data are shared with us, are accessible via RDF, via relational databases. There are a lot, of course, of relational databases sharing data, and XML data. So each single model has different ways of accessing, querying data, and then so we need to instantiate our systems differently if we are talking about a graph database, a relational database, or XML. So for each one of these models, we selected a relevant application domain, a relevant use case, and so it's eagle-eye for RDF, a U for database, BPS, the guide to pharmacology for the relational model, and the digital archives in the encoded archival description format for the XML. So now we are going to see the details about each system and each use case. So the first one is RDF. I know it's quite unusual to start with RDF. Usually you expect to see relational XML RDF, but somehow the system we implemented and we realized for RDF it's simpler than the others, so we start from this and then we go through increasingly more complex systems. So here you see the two references describing the RDF system for citing RDF data, and most of this is a joint work with Abdul Alawini, Bishan Cheng, and Susan Davidson from University of Pennsylvania in the United States. So basically, the use case we consider is eagle-eye, and eagle-eye is a resource discovery tool. It is built to facilitate translational science research, and it's developed by a consortium of universities financed by the NIH in the US, and Harvard is heading this consortium that is comprising basically all of the most important universities in the US. And the end users are researchers who wish to share information about research resources like core facilities, IPS cell lines, software resources, and so on. And the data is stored and distributed as RDF files. So we're dealing with a distributed graph databases. Basically, each university has its own graph database, and then we have federated databases that provide unique and centralized access to all this distributed data. So if we take a look to the eagle-eye web page, so here this is a screenshot of the eagle-eye system. So we see that we can search for resources, and here we see a resource which is a mouse, anti-mouse, gamma, whatever. It's basically an antibody reagent, and we see that there is, if we zoom in, we see that there is this cite the resource button. If we click that button, we have this pop-up window showing the unique identifier, basically the DOI or the URI for this resource, and a click here for citation examples. So if we click there, we are sent to a page showing us where the relevant information about the resource is. And so basically then we have to understand this page, then go back to our resource and select all the relevant information. Here I highlighted the information. So basically the title, the location, the institution. Then we have to go back to the pop-up window and retrieve our URI and then build the reference following the format that we like. So also here we may have some inconsistencies. So here you see that basically they say that they want to cite the data, but there is only a manual way to construct the citation. So what we did is to automate this process. And to do this, basically, here now I show you the main components of this system. We start from the cite this resource button. So when we start from here, basically we have the URI of the resource we want to cite. Then, starting from this URI, which is called the Eagle ID, we go through an RDF citation model that we will see in the next slides. And from this model, we create a machine-readable citation in JSON format. Then we go through a citation formatter that creates a human-readable citation. So at this point, the users have a human readable citation that they can use for whatever reason they have, and this human readable citation is connected to a machine readable citation. Then we have the dereferencing part. So basically, if we want to dereferentiate a human readable citation, we go through a parser, we reobtain the machine readable citation, and then here we have the versioning module. The versioning system, basically, the Eagle Eye data is not versioned, so we developed also a versioning manager to deal with different versions of RDF data, and basically now we are able to retrieve the correct version of the cited data. But I'm not going to describe the versioning system. It's out of the scope of this presentation, but you can find the details in the paper, of course. So then afterwards, after querying the versioning system, we get the original cited object. So this is the whole process. So how does the system work? And the main part is the RDF citation model. So here we see that in the top part of this drawing, we see the versioning system and the curated database. And then we have the DBA, which is the database administrator, that has to define citation views and citation policies. We will see what they mean. But basically, the work of the DBA, which is done offline, is to say, okay, taking this database, I know that the most frequent queries are this, or the most relevant part of the database is this and this, and the DBA defines a view over this data and connects a citation to these views. So the work that he has to do is just to say, these are the most relevant parts, and these are the citations for the most relevant parts. Then what we do is to use these views to provide citations for more general queries. So here you see two main components, which are the query rewriting module and the citation generation module. But let's see an example. So here we have a very simple RDF dataset composed by just 3 resources, resource 1, 2, and 3, and you see that resource 1 and 2 share one institution, resource 3 is from another institution, they share type, and so on. So now we have an author of a paper asking a query to the curated database, and this query is like a select where he looks for anything connected to cytometry that I do not know what it is, but basically we see from the data set that resource 1 and resource 3 are about cytometry, right? So we expect that the result set is something like the one that we see on top of the slide, and basically the system is going to return resource 1 and resource 3. At this point, the author wants a citation for this result set and for his general query, right? So what we do is to take our data set, and if you see now, the data set is annotated, and it's annotated with some views. This set with the dashed lines that you see, those are sets. So basically, these sets of resources are defined by the DBA offline. So basically, the DBA defined one view for resource 1 and one view for resource 2 and 3, right? And these views are related to some citation queries. So basically, citation queries are defined by the DBA, and these queries retrieve the relevant information for creating a citation for the view, right? Okay. So at this point, we have the query rewriting module, and what this module basically take the result set or the query, it depends, and try to rewrite this query with the views. Basically, what we want to do is to obtain the same result set without using the user query, but using the views we have. And once we are able to reproduce, basically, to reobtain the result set with the views, we know that those views are relevant for the result set and can be used for creating a citation, right? So in this case, we see that resource 1 is in the set of V1 and resource 3 is in the set of V2. So we know that we have to use CV1 and CV2, which are citation queries to create the final citation. So here we see that v1 led to cv1 instantiated by resource1, and that the citation for this is grant G version 12 and this name with this DOI. And for v2 is the same author, the same version, but different name, different DOI, of course. So at this point, we have one citation for each return resource. But of course, the user wants one single citation for the result set, of course. So now we go through the citation generation model using the citation policies. And these policies define how we put all the citations together in order to get the final citation for a user. And so we may have different policies like union. This is the typical policy we use in our text. It's like just we take the union of all the citations and we get the final citation. So in this case, we see that if we take the set theoretical union, grant G, the author is the same, the version is the same, and then we have the list of names with DOI. So the final citation will look like the one you see below in the lower part of the slide, right? So basically, this system works in this way. The DBA has to define some views, and these views have to be defined by looking at the most frequent queries or the most relevant part of the database. Then the DBA has to specify a citation query for each view or a citation for each view. Moreover, the DBA has also to specify some citation policies. Once we have all this information, the work is done, basically. And if we do not add new classes or resources, we do not have to update our system. And even if we add new resources, everything is good to go, and we do not need to change our citation system because the system is able to use all these basic views to create the final citations. Of course, to have this system working, the DBA has to ensure that the system is versioned. The system, I mean the database, is versioned and enable also differentiation of citations. So for RTF, with this system, basically we have the DBA has to do some work because he has to define the citation views and citation queries. For XML, we started from another point of view, saying, okay, let's assume that we do not have any resources or the competency to define the views and to define the citation queries. So we want to provide a citation system able to provide citation snippets without any prior information, just starting from a bunch of citations that we have. Okay, so for XML, we developed this system called the Learning to Cite framework, and we used that and we tested that with digital archives. So let's see what we mean as an archive. An archive is a complex structure composed by shelves. One shelf has folders, each folder has envelopes, and in envelopes we have documents and so on. So basically an archive has a tree structure, and basically this hierarchy is used to maintain the relations between all the documents within the archive and keep the context. But when we deal with digital archives, basically we deal with trees, and these trees are encoded in XML files. And the standard for digital archives description is the encoded archival description, or EAD. And here we see a typical, on the left, a typical archival structure, a very small one, and then on the right, the XML file. So basically what we need to do is, given one archive, given a big XML file describing all the documents and all the categories and all the divisions of this archive, and a general query or a node within the archive, we have to provide a citation for that node or for that bunch of nodes. So what we have to keep in mind is that a single EAD file encodes a whole archive. So we have big XML files with deep hierarchy. and that these EAD files are quite heterogeneous one with the other. So we have heterogeneous files within the same collections and also across collections. So each single archive, we can assume that the rules, for instance, defined for a single archive can be reused for other archives. And often we have textual elements within the XML elements containing HTML tags, so it's not very easy to process these files. And basically every element and attribute of the XML file we are dealing with is a potential citable unit. So we may need to cite every single attribute or element of an archive, right? So here we have some statistics or some collections that I considered for these tests. And so here now, basically we are considering the Library of Congress collection, which is composed by 2,000 archives. And we see that we have up to almost 200,000 nodes for a single archive with 18 level of depth. And the typical size of an archive is 10 or 15 megabytes. So for an XML file is quite big, right? So here we have a human readable citation. So if we want to cite a node within an archive, this is what a typical citation looks like. I took this citation from the guidelines of an archive that I consider. So correspondence and this date is the citable unit. But if we want to cite this, you see that is not very informative. So we need to add contextual information. And this contextual information are taken from the ancestors of the citable unit in this archival tree. So we have the elements of legal theory that is in books, the box, the part, other boxes where you basically all the information that you need if you go in the archive and you want to find the citable unit. And then in the end, we have the persistent identifier of the EAD file, right? So the key point is that all this information can be found in the XML file. The problem is that it's very hard to find this information within the file if you do not know how to process and to query XML. And this is how basically a machine readable citation, and it's a conjunction of XPaths. And you see that this is impossible to ask for a user to provide this citation, right? It's not possible. Every single XPath that we have seen leads to basically a human readable snippet connected to it. But what does the user see? This is the typical web page of an archive, and so we see here highlighted in orange the correspondence, the citable unit, the thing that we want to cite. So from here, if I want to cite this, you see all the information that I have to collect within the page. I have to go up and see that this is within book, box 135, in part 2 on the right, writings and so on. But then I also have to change page and to move to another tab and select other information that are relevant for the citation. So it's impossible to ask a user to provide this citation manually. And see that here I consider the Library of Congress, which provide us with one of the best websites. So this is very good, but we have also other websites that are not that intuitive. Anyway, so what we want to do is, given an XPath identifying a specific node within an XML and a dataset in an EAD file, we want to generate the human readable citation and the machine readable citation. To do this, we do not want to ask the DBA to provide us with anything. Why? Because especially in the digital archive domain, resources are very low. We cannot ask them to invest hours or money in providing us with citations or views or whatever. It's very unlikely for this to happen. What we want to do is, okay, you have these files, you invested a lot to describe these archives, and you have a bunch of citations because you just provide me with a bunch of nodes and you tell me this node is cited this way, this node is cited this way, and the citation is just a textual citation, so no technical expertise is required. So our idea is to use this set of citations and nodes as a training set for a machine learning algorithm that basically is going to learn a model from this citation, and this model is then used for providing citations for other nodes that we have never seen before. So we learn from a sample data, human readable citation, get a citation model out of it, and generate citations. This requires a very low effort and resources to data creators and curators, and handle data heterogeneity, because this model is able to adapt to different structures and archives and XML in general. So I'm not going into the details of the model that I define, because that would require a lot of time and technical expertise, but what is relevant are the the key components. So you see that we start from the component 1, which is training data, human readable citation, and XML file collection. So here is where we have the work of the DBA or the data curator of the archivist. It depends by the context we are considering, right? Then we have a model which is called the learner. So we give this training data to the learner, and we obtain the third part, which is the citation model. This citation model is basically a template and has a part about the structure of the XML and a part about the content of the XML. And once we have this model, we can use this model in our citation system. So you see that the point 1, 2, and 3 are done offline. We obtain the citation model, and what we can do is to test our citation model and see how it works. And when we are satisfied with our citation model, we are not going to change this citation model in the future, unless we are changing consistently our dataset. So once we have this model, we plug it into our citation system that you can imagine it works pretty much like the RDF system we have seen before. So we are given with the text data, but the text data are basically the user queries. And for XML, user queries are XPath or X queries. And then with the system and the path, we just produce the output citation. This system works, especially for digital archives, we do not expect users to ask an X query or an XPath. But we expect users to click on a web page and say, okay, I want to generate a citation for this node, or we expect the user to click a bunch of nodes and say, okay, I want a citation for all these nodes, right? But it's quite easy to connect each single node selected by the user with the XPath identifying that node, because an XPath basically within an XML file is a unique identifier for that node. And once we have these XPaths, we are able to create our citations. We did this, basically we tested this system for in the digital archive context, and we have seen that we just need up to 20 text citations, and to be able to create citations for an heterogeneous and for basically all the nodes within the archives with a precision of 90%. So it means that we are able to use very precise citations with very, very low effort. And we have seen that if you provide the system with 30, 50, 100 citations as a training set, the results do not change much. So basically, we are pretty much sure that for the digital archive context, where we have a quite high heterogeneity from file to file, the system is pretty solid. What we want to do in the future is to plug in the citation policies that we have seen before also in this XML system, in order to be able to combine citation of different nodes into a single citation. And also we want to test this system in a different domain, for instance, pharmacological domain, methodological data, or physical data domain, whatever, because we want to see if we need more citations, for instance, or if we need less citations because the context is less heterogeneous. So this will be very interesting to test this system in different domains. And all the system and the model, everything is open source and available on my web page. And you see all the data in the slides. So, and also the data we used for tests are available. So you may see how you have to format your data to use the system. And last but not least, I have 10 minutes, so okay, I'm quite on time, is how do we cite relational databases? And this is quite a hot topic because you know, most of the data and scientific data we have are available as relational databases. And for this case, we used as a use case the IUFAR BPS pharmacological database. There are two papers that you should reference to if you want to dig into details, and one is CIDR 2017 and the other is PODS 2017, and this is a joint work with Susan Davidson, Daniel Deutsch, and Tova Milo. Susan is from the University of Pennsylvania, and we work together also for the RDF part, and Daniel and Tova are from Tel Aviv University. So in this case, the citation generation problem can be formalized like this, and now I tell you. What you should keep in mind if you are not really into database details, let's say, is that this system works similarly to the RDF system we have seen before. Basically, what changes is how we define views, right? Because for RDF data, views are defined, for instance, using name graphs, or like using those sets that you remember you saw for classes. Here, views are defined as queries. So a view in a database is basically an SQL query, right? Or a data log query, whatever. So we expect the database owners, the database administrator, to provide us with a bunch of views, like before. So here we go back to the other case where we ask some effort to the database administrator. And the views are connected to frequent queries. And for the IUFAR case, we basically ask the database administrators to provide us with the queries they already have, because they have queries to create the web pages of their website. So basically, when they create a web page, basically that is a relevant query, a very frequent query, and we use that query as a view, right? And then we use these views to provide citations for general queries. So the problem becomes in this case, given a query queue, posed by a user, can we rewrite this query by using the views? So in this case, this problem is well studied in the database community. You can see here a bunch of very, very relevant and authoritative references. And this problem is well studied, but is also hard from a computational point of view. We have to consider that in our context, this may be tractable. Actually, it is tractable because we have created a system that works. So it's tractable, but it's not easy to solve. What we introduced here is the concept of parameterized views. So basically, as you see, this is the tree defining the structure of the database we are considering. So we have the root, then we have the families of the drugs we are considering. Each family is connected to an introduction describing the family and targets. Then we have tables and so on. But basically what you see is that each single node of this tree has a different citation. So what is the effect of these parameters on a view? Basically, if you take the view that I show you here, V1, this view is simple. It's defined over a general relation of the database. The relation is family. And as you can see in this example, this relation has an identifier, 1, 2, 3, 4, 5. And each identifier is connected to a name, the name of the family, CLR, molecule, whatever. And then there is a type, Z, G, CR, and so on. But then we also have a parameter, and the parameter is defined by this lambda operator in the beginning of the query. And this lambda operator says that we are instantiating we are parameterizing each single view by the ID, F. So we expect to have, as you see here, a single citation for each tuple in this table. So if we use V1, we have a citation for the tuple 1, for the tuple 2, for the tuple 3, and all the citations are different. Then we take another view, and this view is exactly the same as V1, but we removed lambda f, the parameter. So this view is not parameterized. So it means that this view is connected to a general citation. So here we define a citation for the whole family. So basically, we see that if the user is asking a specific family, we answer with V1. If the user is asking all the families in the database, we answer with V4. So to specify a citation, we have three components: the view definition, the citation query, and the citation function. The same as for the RDF system. The citation query retrieves the information relevant to create the citation, and the citation function formats the information we retrieved with the query and creates the citation. This is basically a triple, and we call it a citation view. All the queries and views are expressed in Datalog, but you can imagine them expressed in SQL or whatever. It doesn't change anything. So let's see one simple example. Do we have time? Yeah, a few minutes. So in this case, we see a very, very simple relational schema. So here you have three relations: family, family intro, and person, and then other two relations, FC and FIC, that basically are connecting family and family intro with the person that contributed to the family or the family intro. Then we have some views, V1 and V2. They are parameterized on the ID for family and family intro. And then you see that these views are connected to citation queries. We are not going into details, but you see that these citation queries basically just retrieve the names of the person, of the people that contributed to a family or to a family intro. So what we can do is basically, is to use these views to answer a general query. And to do this, we have to find a match between the view and the query. But we may have an exact match, so we have exactly the view answering the query. And that's it. Then we just use the citation query and we have our citation, like in the case of the RDF, right? But often it happens that we do not have a single view answering the query, but we have to use a conjunction of views to answer our user query. And so what we have to do is to basically put the views together. So for instance, here we have a simple case where we have Q1 that can be answered by using V1, because we can rewrite Q1 that you see in yellow here, just using V1 that you see in the green part. So then we just instantiate the view and we obtain the citation. But if we cannot do that, we can use, and here I'm going very fast, just telling you that there exist different policies to combine different views for answering a query. And we can use a joint of tuples or an alternate use like unions. And to do this, we use the formalization used for provenance, and basically we use provenance summaries. And this provides us with all the theoretical model that we need to create the citations. This one is too much detail, so I'm just going to skip it. Just use it as a reference if you want to go through these details. But basically what I want to show you is the example of an output citation. So here we have a view definition, a citation query, and a query, right? So here it's immediate to see that we can rewrite Q1 with the view V1. So we have Q1 prime that is using V1. And we see that this query is returning this result set, just one tuple. And basically the citation is the one that is produced by using the citation query connected to the view, which is like a bunch of names, the name of the family, when it was last accessed, and the name of the database, and then details about the query. Actually, the query itself. Here is a data log query, but you can imagine an SQL query. This one is a more complex example where we have this query, which is a join between family and family intro. All right. If you see the view definitions, we do not have a view exactly matching this query, but we have to use both V1 and V2 for rewriting Q1. As you can see it here, that Q1 prime is composed by the conjunction of V1 and V2, right? So here, the result is basically the same, only one tuple, but we have also the text of the family intro. And, sorry, okay. The citation, in this case, is composed by two citations. The one answering to V1 and the other one of V2. So what we need to do is to combine the citations. And we do that, sorry, by using the provenance semirings that I described before. So using basically the citation policies we have seen for the RDFs. The big picture in this case is that we need to be able to define views for a database at the schema level. Then database users basically need to have citation served up as they extract data through queries, and then we need to be able to differentiate these citations to give the data back to the people asking for that citation. So here we have some computational challenges. So we are digging and investigating how to implement this system for the relational databases. So implementing it at the schema level or at the instance level. We have pros and cons for both implementations. The good news is that now we have 3 different instantiations of the system. One is totally schema level, another one is totally instance level, and then we have an hybrid system. And we have basically all these 3 systems are returning the same citations for the same queries, but depending on the context, one could be preferred to the other. And so this is something that I would like to discuss with the experts and domain experts. Say, okay, you have this database, let's see what system is the best for your situation, for your context. So final remarks, and I'm concluding. In general, automatic generation of citation snippet is overlooked in general by many scientific databases. Why? Because it's a complex problem, because prior of generating the citation snippets, we need to have a version database, we need to be able to differentiate citation, we need to be able to uniquely identify the data, retrieve the data that we cited, so basically all the other recommendations of the RDA, right? But once you have done that, you are in the perfect situation to go through and implement also the automatic generation of citation snippets, and because this is a key aspect of data citation. But citation systems need to be customized for specific domain. And the last thing is that we are looking for interesting and challenging data sets to work with, basically new domains, requirements, users, and see if our systems can be used as they are for your domain, or if we have to change them because they are not well suited to answer to your requirements. So that would be a good research project. If you have interesting data, you are interested in generating citation snippets, please write me and let's start a conversation about this, because I think we can do great work. And so lastly, these are the references. They are all full text. The full texts are available on my websites, and so you can download them, read them, and ask me details. And that's it.
Thank you very much, Maria. That was a fantastic presentation. And I guess you might be swamped with requests for actually fine-tuning the system to specific domains. So I guess there will be quite a lot of people interested in getting such a citation system implemented. Starting with
happy to work with them.
I've got one question listed from Eli Papadopoulou, basically asking where you find the policies that you were referring to. And Eli, I will hand the microphone over to you so you can discuss with Maria.
Okay. So The policies, for the cases I presented, for the Eagle Eye dataset, for the RDF, we discussed with the owners of the database at Harvard University, and they told us, okay, I think that the union of citation for single resources is the best way to do that for our domain. For a UFAR, same thing, we discussed with database owners, whereas for the XML, the system I developed, in this case I worked alone, I worked with digital archives for years, so basically I defined the citation policies by myself. So in that case I would like to work with different XML datasets to see how we can adapt to different policies. But basically they must be provided by domain experts or database owners.
Ellie, does that answer your question? Ellie, is that okay?
Okay. I don't hear anything.
Okay. Okay, the microphone seems not to be working, but
okay.
Looks like we've answered the question. Okay, yeah.
Okay.
Here. While we're waiting for the questions, I've got two questions, because you mentioned for your learning to cite framework that, you know, with like 20 to 30 training samples, you get around 90 or above 90% correctness. So
yeah.
My question is, what kind of mistakes do you find? So on the non-correct citations, is it that something wrong would be cited, or is it more about an incorrect formatting that would not 100% comply to the policies, but still be formally correct and identify the right unit? Or
no, they are not format errors. Also because I do not consider the formatting issues in this case. They are there are three different kinds of error. The first one is repetitions. So you may have the same information repeated twice. This happens because, for instance, the title of an archive, the name of an archive, usually is repeated in many nodes. So in these cases, it's quite hard to prune everything. So repetitions occur. Another case is that you may have one element which is redundancy, the first. The second one is that you may have something which is not relevant. It's not wrong per se, but is not needed somehow, you know, it's something more. So it's relevant for the, I mean, it's about the citable unit, it's about the archive, but you can live without that. And the third case is that you miss a piece of information. So in that case, you, for instance, need the date, and you do not have that. This is the most dangerous error with the learning to cite framework. So basically, with that framework, you do not have much work to set up the system, but you ask some work to the users because they have, for instance, to delete repetitions, or that's it, basically, because they couldn't know that something is missing. But luckily, it's not very common, but it happens. I think that you can provide another learning module after the generation of the citation. For instance, if you have this system running in a real environment, then you can learn and see what users do. For instance, expert users. If they delete a part of the citation, if they add a component, then you can refine your model somehow with a feedback. But I do not have this part because the system is not, for the XML, is not actually used. So this is something I would like to do.
But it's basically only the third error that is really causing some trouble, because the other two are providing spurious or additional information, but not causing any harm or deficiency overall.
Exactly. The last one is the most dangerous because you may miss relevant information. What I've seen is that you have the key information, you always have them because they are redundant in the datasets, but you may miss something. Yes, it's the price you have to pay for when you use machine learning.
Sure, but if that error is not so frequently, if most of the errors are, you know, repetitions or something in addition, then that's actually fine. That doesn't harm overall the performance.
Yeah, exactly. Yeah.
And for the other example that you had on the relational database, where you were require a priori the definition of views in order to answer it. Could you imagine applying something like your learning to cite framework to such a setting where you provide the framework with, what is it, the query, the table definitions, the attributes that are basically in the various columns. So you have the schema, the table names, you've got the query, and citation texts, and learn it from that on. So basically, instead of going back to views as an auxiliary mechanism, going back to the raw tables as you are doing right now when you're combining views, and just learning which elements and which schema elements to use for generating the citation?
Absolutely. You can do two things. You can do learning to cite framework. I mean, you can learn everything, and then basically you do not use the query writing module. So basically you have the citations and you try to learn and you provide the citations for the relational model. That's something I want to try and work on. It's a little bit more difficult because you know, an XML is a tree, and when you have a tree, computationally is much better, right? Whereas with relational databases, you may have loop, you may have all sorts of stuff, and also with RDA, so it's more difficult. But what you can do is something hybrid. So basically, you do not ask for views and citation queries to the database administrator, but you use, for instance, in the case of a UFAR, the citations you already have and the web pages you have, because the web pages are created starting from queries, right? And every web page is connected to a citation. So we can use this information to learn a model to create views. And once we have the views, we use the query writing model to create citations. So basically, you do not ask the DBA to work because you learn the views. It's hybrid. But this could be halfway for relational databases, given the complexity of the structure of most of relational databases. But also in the first case, so a system totally based on machine learning is something that I really want to explore. I'm just waiting for the good example to work with and the good requirements from the community.
Absolutely. So this makes sense. I mean, something I noticed is that the examples that you picked are always rather complex settings where you have, you know, complex hierarchies or where you have multiple tables that need to be joined. Something that we find quite frequently is that research databases consist of rather simple schemas, which are sometimes even one single flat table, basically, with no joins. So just subselects on basically huge CSV file type things, for example. And in this case, I guess the situation would be much, much simpler.
Well, yeah, absolutely. In that case, well, that's great. I mean, if you have a simpler data set and simpler queries, you know, much of the complexity is taken away. So one, you can define a machine learning algorithm because it's simpler, or you can also use the query writing model because, you know, it's very fast when you have such a case. And now I do not have a paper and I cannot speak about that work, but basically I hope that in the future I can present a system that we have just developed, working also with simpler cases where we consider, for instance, partitions of a table, where you say, I want just to cite these two columns of this table, or I want to cite these two tuples. I do not have joins, I do not have cross products, aggregations, whatever. It's just one table. I want to cite the whole table, one tuple, a bunch of tuples, or a bunch of columns, or combination of those. And in these cases, you see that the complexity is going is low, and so you can have also, you know, rules. You can infer the citations because even though usually these are complex tasks, for this setting is not that complex. So yes, we are working on this.
Yeah, that looks fun because I think a lot of many settings have such rather simple, well, simple in inverted commas, but still way lower complexity problems, and that might solve, you know, a lot of situations, the famous 80-20 rule, so to speak. So I'm looking forward to that.
Yeah.
Great. So let me see whether there's any other questions by any of the participants. If not, I would again like to thank you very much, Maria, for giving this webinar.
Thank you.
the slides and the recording available as soon as we've got it converted and uploaded. And I'd like to thank everybody who participated and listened to this webinar. Thank you very much, and we'll announce the next webinar as soon as we've set up the scheduling. So keep following the mailing list. And if you've got any implementations, any prototypes running that implement the dynamic data citation recommendations and would like to present it, please drop me an email and we can schedule a presentation. Again, thank you very much, everybody, and have a nice morning, afternoon, evening, night, depending on where you are from. Thank you, and bye-bye.
Bye-bye.